Hey, welcome to your Unit 12.1 Equilibrium Constant lesson. So this is the beginning of the end, folks. Yes, it's your last chapter. So the equilibrium constant. Of course, we've talked in Chapter 11 about what an equilibrium is and how to affect that equilibrium to take better advantage of the situation, if we want to produce more of the reactants or more of the products, for example. So now we're going to talk about the actual constant behind that equilibrium situation. So of course, as usual, we always try to find shortcuts so we don't have to experiment again and again and again. Rather, we want to do things on paper so we can determine ahead of time what changes we should bring to an equilibrium in order to get what we want out of it. So now we're going to go more into the theory, so to speak, more into the equilibrium law. So let's look at the following reaction. We have two reactants, A and B, with their coefficients, small a, small b. Two products, C and D, with their coefficients, small d and small c. So the way the equilibrium law works is that we take a look at the concentrations of the substances. So again, because we're talking about concentrations, we're only looking at gases and solutions. And we will do concentration of the products over concentration of the reactants. And those concentrations are expressed to the power of their coefficient. So if we take this theoretical reaction, we get, for example, concentration of substance C to the power of its coefficient times concentration of substance D to the power of its coefficient over concentration of reactant A to the power of its coefficient times concentration of reactant B to the power of its coefficient. So again, products over reactants is the general approach that the constant uses. Now, what does that constant tell us? Again, I'll show you later. It's going to allow us to predict if we change one or several of the concentrations, which way will the equilibrium shift, so we don't have to actually test it, so we save time. Now, when we talk about reactants and products, we're always referring to the forward reaction. So again, these are the products, but for the forward reaction, these are the reactants for the forward reaction. So if we wanted the constant for the reverse reaction, we could do it two ways. Either flip the fraction over, because these, the A and B, if we look at the reaction, would become the products, and the C and D would become the reactant, so it would be the other way around. So I would have products, if I'm thinking reverse reaction, I would have products over reactants. I would have the opposite of this law. So the simplest way of doing it is calculating Kc for the forward reaction and then doing 1 over Kc to get the constant for the reverse reaction, the equilibrium constant for the reverse reaction. So you have another example here with actual substances. So I have H2 plus I2 gives me 2HI. So for the forward, I'm going to have products squared, so the HI squared because of the coefficient here, over concentration of H2 times concentration of I2. And for the reverse reaction, well, I would have the opposite equation or fraction. I would have H2 times I2 over HI squared. So again, the faster way of doing this is calculating the Kc for the forward reaction and doing 1 over the value to get the Kc of the reverse reaction. And again, Kc means constant of equilibrium. This is just a default letter. It doesn't really mean anything. Okay, so given the following reaction, what would be the equilibrium law? Well, again, we said it's always products over reactants. We have K, if I just put the general format, is equal to concentration of the products over concentration of the reactants. So in this case, we would have concentration of CO2 to the power of 2. Now, tin is a solid. It cannot be expressed as a concentration, so I disregard it for the equilibrium law. Over concentration of my reactants. In this case, this one being a solid, I don't take into consideration in the calculation of the constant because, again, it cannot be expressed as a concentration. So I'm only looking at this one. So concentration of CO squared because of the coefficient over here. So that would be the equilibrium law. So always products over reactants. And since we're talking about concentrations, we only deal with gases and solutions. The rest we disregard. Pure liquids, pure solids, we disregard. Okay, moving on to what is the value of Kc, or what does it mean? Again, it's products over reactants. But what does the value really tells us? It tells us at what point did the equilibrium actually set in. As I explained to you, the equilibrium doesn't set in right away. So we always have, if I just draw a little graph quickly, we always have the reactant that starts reacting, right? Or the reactants, but let's say I just draw one. So it starts reacting, the products are produced, and then eventually the reactant continues to react and produce the products, but the problem is, or the situation is, that the products start turning back into the reactants, and that creates kind of a situation where the two reactions cancel out. So that's where we have the equilibrium, right? So before that, my reactants are reacting, my products are being produced. Now, it could be that in a certain situation, my two substances will reach an equilibrium whereby both substances are at the same exact concentration. But it could also be, like in here, a situation whereby my reactants are depleted much more than the products that appear. So in other words, the amount of reactants that I have present is lower than the products that I have present, and that's when the equilibrium sets in. Or I could have a third situation whereby my reactants react and the equilibrium sets in very quickly. So the amount of products produced before the equilibrium is attained is very low. So this being my reactants, this being my products, you can see that my equilibrium kind of favors, in a sense, the amount of reactants. I have much more reactants at equilibrium than I have products. So in this case, the reactants would be favored at equilibrium. In other words, I have more reactants. Here, neither is favored. So my reactants, the amount or the concentration, is equal to the concentration of the products. And in this case, the products are favored. I have much more products than I have reactants at equilibrium. So the products are favored. So that's what your constant tells you. Is it this situation? Is it this situation? Or is it this situation that you have at equilibrium? So if we look at the mathematical ratio, if my Kc is equal to 1, that means that the number here and the number here are the same, which gives me an equilibrium constant of 1. So that would be this situation over here. I have as much reactants as I have products. If my constant is greater than 1, that means I had a bigger number on top, so my products are favored at equilibrium. So I have more products than reactants at equilibrium. So it's the situation here. And if my constant is smaller than 1, that means this number here was bigger to give me a constant that is below 1. So if I have more reactants, I have this situation here. I have more reactants at equilibrium than I have products. Okay, so that would be here, if I just write it with a different color to make it clearer. So this one would be Kc smaller than 1. This would be K equal to 1. And this would be K greater than 1. So that's what your constant means. That's what this value here tells you. Okay, now we know that a change in pressure, volume, concentration, whatever, will affect an equilibrium. But that constant here will never change unless the temperature changes. So this constant is for a specific temperature. So every time a constant will be given to you, it'll be given to you at a specific temperature. Okay, and only the temperature can change the value of the constant. Otherwise, I can change my concentrations, I can change the pressure, volume. This value will not change because of pressure, volume, or concentration. Only temperature will change it. and it will change based on what we saw before with Le Chatelier. So if, for example, if I look at this equation, this reaction, I can see that the reverse reaction needs the energy. So if there's an increase of energy, I'm adding energy that's favoring the reverse reaction, we said. So the reverse reaction means I'm going to be making more reactants and I'm going to be depleting my products. So these amounts are increasing, this is decreasing. So how's that affecting my K? Well, this number is becoming bigger, so that means my K is decreasing, which is what we have over here, right? So if I increase the temperature, I'm favoring the reverse reaction, which is decreasing the value of K. So if you understand Le Chatelier's principle, you'll be able to understand these items here. Just make sure you take a look at them to make sure you master all this and that it's clear to you. Now, how do we calculate the concentrations at equilibrium? It's all nice that we have an equilibrium law, but what do we do with it? So let's pretend we have the following problem. We have the following situation or equation or reaction. I'm giving you the initial concentrations and the final concentrations of both. So from there, you're able to calculate the change in between. From now on, to work with an equilibrium situation, we're going to work with what we call an ICE table for ICE, or I for initial, C for change, E for equilibrium. The way this works, it allows you to kind of complete the information that you may be missing. So you have the reaction on top, you have the line for the initial concentrations, you have a line for the actual changes, how much reacted for the reactants or how much was produced for the products, and therefore at equilibrium, once nothing changes anymore because the two reactions are canceling out, what are the concentrations present? And these are the concentrations that ultimately you would plug into your law, like this one. So let's take it one step at a time. So I have this situation here. So the information is already written. I have 1 mole per liter of H2, 1 mole per liter of I2, and of course at the beginning of the reaction, before I attain equilibrium, there is zero product. There's nothing. We haven't started the reaction yet. Then we discover that at equilibrium, so when we don't observe any more change in the system, these are the concentrations present. Well, what happened in between, it's easy to do the math, right? So we're saying we started with 1 mole per liter, and at equilibrium, we only had 0.22 left. So how much was lost? There was 0.78 mole per liter that was lost or that reacted. For I, 1 minus 0.22, that means I also had here 0.78 that reacted. And for the product, I started at 0 and ended up at equilibrium at 1.56, which means I had 1.56 mole per liter that appeared. Now, the reason why I put this box in red, the change line, it's because this change line is always linked to your coefficients. So you can do stoichiometry with these coefficients and with these numbers here, they will respect your ratios. So if you look here, we have 1 for 1, so it makes sense that the same amount reacted. And you have 1 for 2, so it's only normal that double the amount was produced versus what reacted over here. You could do the ratio with H2 versus HI as well. So I have 1 for 2, so I should have double the amount here as I have over here. Now, don't forget to put the minuses or the pluses, because that really shows that you have a product, the substance was produced, and a reactant, the substance reacted, was depleted, disappeared. So again, you have more examples on pages 316, 317, which I will not go over in this video because it would take too long, but if you have questions regarding them, make sure to ask me in class. So again, what's important to remember is that the change line here always respects the ratios, the coefficients in your equation. So now let's take a look at a real problem based on what we know. We can do the following. The decomposition of hydrogen iodide at 450 degrees Celsius. Now, if you remember, I said that when we work with an equilibrium and with a constant, the constant will always be linked to an actual temperature. It doesn't mean you have to use it, it's just extra information they're giving to you, but they're just being thorough in the info that they are giving to you. So, this decomposition of hydrogen iodide, and you have the equation here for it, produces an equilibrium mixture that contains 0.5 mole of hydrogen. The equilibrium constant is 0.2 for the reaction. How many moles of iodine and hydrogen iodide are present in the equilibrium mixture? You are using a 1 liter container. Okay, so what do we do with this? Let's start by writing down what we know. I don't know how much I have of HI. I have X amount. I know that for my products, I always start at 0 initially. I know that I have 0.5 mole of hydrogen at equilibrium, and I know that I'm working with a 1 liter container, so my concentration is 0.5 mole per liter for hydrogen. So here I have 0.5 mole per liter. Now these always use molar concentrations, in other words, concentrations in mole per liter. So here I have a change of plus 0.5, right? If I went from 0 to 0.5, I have plus 0.5. Now I know that my coefficient here is 1 and my coefficient here is 1. And I know that my changes respect those ratios. So if I gained 0.5 here, that means I will have gained also 0.5 over here. If I started with nothing, that means at equilibrium, I'll have 0.5. Now, here it's 2 for 1. That means double the amount reacted. So that means I lost 1.0 mole per liter. So at equilibrium, I'll have X minus 1. I'll drop the 0. You'll see why after. I'll just make it easier mathematically to solve after. So next, what do? I write down my equilibrium law. So my equilibrium law, Kc, is equal to concentration of H2 to the 1 times concentration of I2 to the 1 over concentration of Hi squared. If I replace, I get 0.5 times 0.5 over x minus 1 squared. So now I can solve and find the value of x. Now you know when you have an equation like this, now, oh, the other thing is, sorry, I forgot to tell you, I forgot to put this here. So this is equal to, they were giving me the value of k over here. So it's 0.02. So all this is equal to 0.02. So if we go back for a second to the question, they're asking you how many moles of iodine and hydrogen iodide are present in the equilibrium mixture. They should say with concentration, really. So we'll answer with the concentration in this case. So what concentration of iodine and hydrogen iodide are present? Well, the hydrogen we found already. The iodine, sorry, we found already. It's 0.5. Now all we have left to find is x minus 1, what it is, which will correspond to the hydrogen iodide concentration. So all we'll do is solve for this here, and that gives me 3.5. So here is x minus 1 is equal to 3.5. So which means that this over here, if I just replace, is 3.5 mole per liter. If they just want the moles, knowing that it's in a 1 liter container, we can say it's also 3.5 moles. Okay, so that's how you solve the problem. Now it could be that you have something more complicated to solve, and here's a little reminder of how quadratic equations work. I'm not going to go over it, you've done that before, but it'll be in the notes, so if you forget, this is what it is, so just take a look at it again. Now do not forget, you get two values of x. Now, since you're looking at concentrations or number of moles or quantity of matter anyways, this cannot be negative, so you always drop the negative concentration, you only stick to the positive one. So there you go. That's the end of the lesson. See you around for the next one.